Hi everybody, welcome back to Algebra. Today we are going to be talking about matrices. So first of all, we're going to talk about what they are, how they work, how they're organized, and then we'll talk about how to do some operations. And by operations, I mean how do you add matrices, how do you subtract, and even how do you multiply. So we'll actually be doing all of 10.1 and all of 10.2 today. And that'll give you a pretty good overview about what a matrix is and how to use one. So what exactly is a matrix? A matrix is a rectangular array of numbers, and the numbers are arranged in rows. So rows move horizontally, and then columns move vertically. So we name our matrix by the number of columns it has. And the way that we name this matrix is we name it by the number of rows by the number of columns. So this matrix has 1, 2, 3 rows and 1, 2 columns. So I would refer to this matrix as a 3 by 2 matrix because it has 3 rows and 2 columns. Then the other thing about a matrix you need to know is that each number inside of a matrix is referred to as an element. So instead of saying the numbers in the matrix, I'm really talking about the elements inside of the matrix. And so the elements have their own way of being referred to. And so usually to refer to an element of a matrix, you'll see the letter A and then a subscript referring to the row number and the column number. So if I were to say A sub 2, 1, this means the element in row 2 and column 1. So A21, if I go to my matrix and I look at the second row, first column, A21 is the number 5. So then if I were to say, okay, what is A32? Let's see, the third row and the second column would be third row, which is right here. Second column, this number right here, 2. Sometimes they'll say, okay, well, what is A23? The second row, third column. Well, second row. But hey, there's no third column, so we would say does not exist. Let's see what else we can do with matrices. In example 1, we're having to take a situation and organize it with a matrix. And really that's what matrices are used for. They're not just random numbers arranged into a rectangle. Usually you'll see them in the form of spreadsheets where you have numbers that represent maybe 2 or 3 different characteristics all put into one thing. So here we have a matrix. Entries in the matrix are numbers of students on a committee. Column 1 lists girls, column 2 lists boys, row 1 lists sophomores, row 2 lists juniors, and we need to find each element A12, A21, and A22 and tell what each number represents. So A12 is the first row, second column. So first row, second column, this number right here, 5. So that means there are 5 boys who are sophomores. This one. Then we need to find, let's get a different color now. A21. That means I need to go to the second row, the first column. That would be the number 8. And that's 8 girls who are juniors. And then finally, A22 is going to be second row, second column, the number 10. 10 boys who are juniors. That's how you can represent data with a matrix. Kind of like the two-way table that we talked about when we were doing probability, where it's really similar to that idea. This is number 12. So if you flip the page and find the number 12, like the practice exercise, this is a question that you might see pop up, something similar to it on the ACT or any other standardized test. But that's how I would solve for this variable, and it has one matrix set equal to another matrix. And so what we have to do is we have to find the values of each variable. Well, if I have equal matrices, then each element is the same as the element in the other matrix in the corresponding position. So A is in row 1, column 1. It's the same as the element in row 1, column 1 of the other matrix. So A in this case would be 4. For this element, the B minus 3, it's in the same position as that negative 3. So I could say that B minus 3 is equal to negative 3 and then solve. So add 3 to both sides, we would get B to be 0. For C, C is in the second row, first column, which is in the same position as that element. So C would equal 6. And then D plus 5 is in the same position as 4. So we can set D plus 5 equal to 4. Subtract 5 on both sides. D is going to be negative 1. Example 2 talks about multiplying by a scalar. So a scalar is a number that is not a matrix, it's just like a constant number. And so what happens if you take a scalar and you multiply it by a matrix, then that scalar is going to distribute to every single element inside the matrix. So that's why you see K times W, K times X, K times Y, K times Z. So in example 2, we have in this matrix C, the rows represent the prices for shirts and khakis. The columns represent the brand, vintage, casual, and distressed. If the sales tax rate is 6%, use scalar multiplication to find the sales tax for each item. So scalar multiplication means I would take this 6%, or in other words, 0.06, and multiply it by the matrix. $100, $60, and $30. Now, the nice thing about matrices is if you have this set up maybe in your computer system or on a spreadsheet, you can type in a formula that will do this matrix multiplication for you. And that's the reason a lot of people use matrices. So we're going to distribute this. But this is algebra, so you do need to know how all of this how it all works. We're going to distribute the 0.6 to each one of these and get, let's see, 0.06 times 75 is 4.5. 40 times 0.06 is 2.4. 25 times 0.06 is 1.5. 100 times 0.06 is 6. 60 times 0.06 is 3.6. And then 30 times 0.06 is 1.8. So what this represents, this matrix represents the sales tax on each item. And it keeps everything nice and organized. So I can look and say, okay, well, the sales tax on the casual shirt is $2.40. So this is how you would see a scalar multiplication on either the SAT, the ACT, or some kind of standardized test. It'll set up, again, two equal matrices, but this time it's involving a scalar. And then it says, what's the value of A plus B? So what I would need to do here is I would need to distribute the 5 and also distribute the 14. So if I distribute 5 on the left, I have 5A, 5B equals, and then distribute the 14. 14 times 20 is 280. 14 times 12 is 168. Then I need to figure out what A and B are. So I can set up two equations. 5A corresponds to the element 280 in the other matrix. So I can set up 5A is equal to 280. Divide both sides by the 5. And A is 56. The other equation I can set up is 5B equals 168 because those elements are in the same position. Divide both sides by 5, and I get 11.2. Or it looks like I have fractions in my answer, so let's make it a fraction. 56 over 5. So if the question asks me, it doesn't ask me for A, it doesn't ask me for B, it asks me for A plus B. So if I add 56 plus 56 over 5, I'm getting 336 over 5. Which is not an option, so hang on, let's look at this. Here it is. There was a division error. So 168 divided by 5 is not 56 over 5. It's 168 over 5. So not this. 168 over 5. Go with this right here. So if you add 56 plus 168 over 5, we will get 448 over 5. Let me write that down. 56 plus 168 over 5, 448 over 5. So I would choose option C. Example 3 deals with adding and subtracting matrices. So to add and subtract matrices, here's what you do. You're going to add the corresponding elements. So if I'm going to add matrix A, B, C, D plus matrix E, F, G, H, then I'm going to add the corresponding elements. So I would add element A plus element E, the first column, first row, and that would be the first column, first row of my new matrix. And then I would add, let's see, B plus F in the first row, second column, and I'd have B plus F, first row, second column. So I've got matrices N and N, and they want to know what is M plus N, and then what is N plus M. So let's do M plus N first. So we're looking at the order. Is the order going to matter? Okay, so for M plus N, I'm going to add -3 plus 6. -3 plus 6 is 3. Get another color. Then first row, second column, 5 plus 5 would be 10. Second row, first column, 2 plus -8 is -6. And then second row, second column, 0 plus 0.2 is 0.2. So there's n plus n. Now, if I were to do this the other way, n plus n, would I get the same thing? Okay, so that means start here and go there. So -6 plus -3 is still 3. 5 plus 5 is still 10. -8 plus -2 is still -6. And then 0.2 plus 0 is 0.2. So does the order matter with addition? No. Order does not matter with addition. The order of the matrices does not matter. Now to subtract, let's see what happens there. So let's first off start by finding m minus n. So -3 minus 6 is -9. And then -5 minus 5 is 0. 2 minus -8 is 10. And then 0 minus 0.2 is -0.2. Now, if I were to subtract these in the other order, 6 minus -3, I'll get +9. 5 minus 5 would be 0. -8 minus 2 would be -10. -2 or 2 minus 0 would be +2 or +0.2. So does the order matter? Yes. So order does matter with subtraction. Well, I can't spell. Does matter with subtraction. The other thing that's important to know whenever you are adding or subtracting matrices is that you must have the same dimensions. So to add or subtract matrices, you must have the same dimensions. So up here, I have a 2-column, 2-row matrix plus another 2 by 2 matrix, and I got a 2 by 2 matrix. Let's write that out. 2 by 2 plus another 2 by 2 is going to give me a 2 by 2. The rows and the columns need to be the same. Now, I don't mean that the rows and the columns need to be the same number. You need to have the same dimensions. So if I were going to add a 3 by 1, I could only add it to another matrix that was 3 rows and 1 column. And then that would give me a 3-row, 1-column matrix. So the matrices can be added or subtracted as long as they have the same dimensions. So here we've got some matrix and we got to figure out which sums or differences can be calculated. So let's go through and identify the dimensions. So P has dimensions. Let's see, there are 2 rows, 3 columns. Q has 1, 2, 3 rows and 2 columns. And R has 3 rows and 2 columns. So R and Q have the same dimensions, but not P. P is 2 by 3, which is not the same as 3 by 2. So we can add or subtract Q and R, but not P. All right. Now let's talk about matrix multiplication. Matrix multiplication is for what you do whenever you're multiplying one matrix by another matrix. So I think this is best explained whenever you have a real situation in front of you, because then you can see, oh, okay, now that's why matrix important is important. So on example 1, we've got a small situation that is a very small situation, but if you can understand this, then it'll help you understand more complex examples. So here we go. We have example 1. How could you organize the weighting of grade information differently so that Oscar and Reagan's finals could be given by W times G? So we've got 2 students. We have Oscar and Reagan, and we have a list of their grades. So it looks like they had a unit test, a project, and a final. And it looks like Oscar made a 90 on the unit test, whereas Reagan made an 80. Oscar made a 95 on the project, Reagan made a 70. And then on the final exam, Oscar made a 75, but Reagan made an 85. Then in this first matrix, we have how all the grades are weighted. So the unit test is 0.5 or 50% of the grade. The project is 0.3 or 30% of the grade. And the final is 0.2 or 20% of the grade. So first of all, let's calculate Oscar's grade. So to get Oscar's grade, I would multiply 0.5 times his unit test plus 0.3 times his project plus 0.2 times the final. So when I do all that, we get 0.5 times 90 plus 0.3 times 95 plus 0.2 times 75. That's an 88.5. Okay. Then if we look at Reagan's grade, to calculate her grade, I would do 0.5 times her unit score, so 0.5 times 80 plus 0.3 times her project score, 70, plus 0.2, which was the final exam weight, times 85%. And it looks like, let's see, Reagan would have 0.5 times 80 plus 0.3 times 70 plus 0.2 times 85, 78. So Reagan would end up with 78 for the grade. Now, it wasn't that big of a deal calculating these 2 grades by hand for 2 students, but just imagine if your roster, instead of having 2 students, it had like 40 students or 45. You certainly wouldn't want to do this 45 times. So we can organize this into, we've got 2 matrices set up. We can organize this so that when we multiply W times G, it will give me a matrix that gives me this information. So it all depends on the dimensions of the matrices that are being multiplied and then the grades that you get. So notice that the W matrix is 1 row by 3 columns. And then the grades matrix is 3 rows by 2 columns. Okay, so I'm going to multiply two matrices. A 1 by 3 times a 3 by 2. Now to multiply matrices, whenever you set this up, order does matter, but to be able to do it, these 3's have to be the same number. They have to be the same. If they are, then that's good. You can go ahead and multiply them. If not, then that product will not exist. Then a 1 by 3 times a 3 by 2 is going to produce a 1 by, let me just get an eraser. There we go. A 1 by 2 matrix. So whatever's on the outside. That's how we get the product. So this produced a 1 by 2 matrix, so 1 row, 2 columns. To get the first row, first column, I took the first row, all these weights, and multiplied it by the first column, all of Oscar's grades, and then I added each part together. So that's what gave me the 88.5. And then to get the second element, I multiplied the first row times the second column, which gave me first row, second column element of a 78. Now the layout of this can get confusing, so you can also do this with a calculator. So if you go to Desmos and you go into Math Tools, so when you go to the Desmos page right here, instead of clicking on the graphing calculator, pull up a matrix calculator, and then you can set up a new matrix. It's just your matrix is going to be, you can pick how many rows and how many columns you want. So I wanted 1 row and 3 columns. Well, not 4 columns, 3 columns. And I wanted the numbers 0.5, 0.3, 0.2. Okay, now I'm going to make another matrix. This time I want 3 rows and 2 columns. And then I'm going to enter the numbers here. I need to erase because I can't see what I wrote. 90, 80, 95, 70. And then 75, 85. Now, if I want to multiply the two matrices, I can just say A times B, because that's how I set it up. And there it is. There's the 2 grades. There's Oscar's grades, and there is Reagan's grades. Now, just imagine how this would look if you had more and more students. You'd have more rows, and then all their grades would come out really nice and neatly instead of having to calculate all that by hand. So let's do a couple more examples. Here is the official rule showing you how to multiply matrices, and it does say that you've got to have the elements of the new matrix are the sums and products of the corresponding rows and column elements. Determine whether each equation may be true for the following matrices. So I've got A, B, and C. So I'm going to enter these into my matrix calculator. Let me pause the video and I'll have that done real quick. All right, so I entered my matrices and I need to see if A, B first times C is the same as A times the product of B and C. So I've got my matrices here. Well, let me see what I'm trying to do again. A times B, okay. So is matrix A, let's see what this product is, times B times C. See what that product is. Negative 24, 12, 4, 48. Now let's try it where I have matrix A times matrix B times matrix C. Are those the same? Looks like they are. All right, so as you're doing these, if you do have to multiply by hand, remember whenever you're multiplying by hand, what you'll do is you'll take, to get, let's see if I want to get this element right here. That element is row 1, column 1. So I'm going to multiply row 1 by column 1, so A times W, and add the individual elements together. So I'd multiply A times W plus B times Y. And that would give me this element right here. If I were to multiply, if I want this element is row 1, column 2. So I multiply row 1 by column 2. So I do A times X plus B times Z. But most of the time, you'll only have numbers, so I strongly recommend the matrix calculator. All right, that should be all for today. Have a